Here I am going to show you how to do approximate analysis of this structure. Very simple structure. Here it says draw the approximate shear and bending moment diagram. So why approximate? Actually this is statically indeterminate structures. So our target to solve this, we will convert this structure into a statically determinate structures. How it is to be done? It can be done following some assumptions. So what are those assumptions? Inflection points are located at 1/10 of span from each end of the girder, and girder axial force is 0. Why 1/10? If we look at here, it says inflection points would occur at a distance of 0.211 from each end of the girder. When it is? If this is, fully restrained. Here it is written here, girder ends are completely fixed against rotation. Then we can say 0.211 L. But here we are assuming that it is only partially restrained against rotation. So inflection point must be somewhere within a distance of 0.211 from each end. Within a somewhat distance of atho from each end. Somewhere within. That is why it is taken 0.1 L. So let's start from scratch. Click on 2D, remove the old one. Right now we can start. Click on geometry, take axis definitions, then you have to put the dimensions here. How to do that? Let's see here the structure first, what it is. This is the structure. It says horizontally it is 10 meter 10 meter and vertically it is 5 meter by 5 meter. So we can take x-axis 10 twice. So what we'll do? Here we'll do say twice 10 meters. Add it. Then go for z-axis twice again 5 meter vertically along z-axis. But make sure this is not numbering ABCD because X was in numbering. So we apply, close it, we got it. Now we have to put bars. As you can see here, there is a bar, so we have to put bar. Click on bar. Start from here. You can put drag, to which case continuously. Say here I can do it continuously like this. Here, then here, then here, then here, then here. Got it. Remove this, drag and click here, here, now again and here. We are done. Here and here, again here, go this. So we are done with this, so close this. Now we have to put the support. There are 3 supports, fixed supports. Click on supports, fixed. Click here, 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 we got supports. Close it. Now we need to provide the loads. like this, 22 kilonewton per meter. So we have to choose first load type. Say we choose the dead load. Close this. Now click here. 22 kilonewton per meter, it is actually on bars, uniformly distributed. So that's what we have to follow here also. Bar, uniformly distributed load, and it is minus 22. Why minus? Our load is downward, but this z-axis is upward. So opposite direction. So we have to put minus. Add here. So click here. Click here. Click here. Click here. We got it. Now we put the loading with the values and click here to see the member. So look at this now. It looks exactly same as this. Now go for calculations. Done. We remove this loading. Results. We see the moment diagram first. Click on MY because it will be about y-axis. Bring something here, parameter, put on levels, differentiated field. We will get our diagram. So this is the diagram we got. See here, moment diagram. What is the value here? So it is not matching because we have to match with this top, this one, only this girder, because here they took that one only, this one only. So here it is 176, but here it is showing 107. Here it is minus 99. Here it is saying 132.30. So it is different. Why? Because this is done by software, and this frame, it was statically indeterminate conditions, and it uses stiffness method to calculate, I mean through matrix analysis. Software program doing like that, and their value is this, and this distance, of course, it is more than 1/10, because we have to take here 1/10, because this question says you look at 1 meter out of 10. Here 1 meter, here 1 meter. It means 1/10. So we'll take 1/10. Why 1/10? If it is fully restrained, it is normally considered that this distance or point of inflection will be 0.211 L. Here it says, if it is fully restrained from rotation, it says here, completely fixed against rotation, then this distance from this end to the point of inflection, it will be 0.211 L. But in our case, we are taking 0.1 L from each end of the girder. So I'll show you how to take that points. So once we put that, then we'll check our this moment diagram again, whether it is coming very close to that value or not. Because also this point of inflection, conversion of this, or considering assuming this 0.1 L means we are transforming our indeterminate structure to a determinate structure. because if you look at when they put a distance here, then this middle part they wrote here simply supported girder. It means determinate structures. Before it was indeterminate. You look at here, see here, this part with two supports here, this part is determinate structure. So we'll do that. So how to do that? Let's remove this moment diagram. Here I am taking it as a bar, not with the section shapes. So where is the nodes? First we click on the nodes. So we have the nodes here. We need a node at a distance of 0.1 L of these positions. So click this bar. Click this bar. We are just okay. Now click on edit. Divide this. Bring here by plane. Now we will take say 1 meter from here. Say I took 1 meter. Execute. Already done because already new nodes are created. Again I am here. Take this point 1 meter far from this end. Click here and execute. It is also done. So we created here and here. Now we need to create here and here. So what we'll do, we will highlight this again. We'll now edit, bring this divide, click here, remove this. Now you bring you this, it will be exactly at 9 meters. Click here, execute. You see, created. Now bring here, click here at a 19 meter. It is showing 19 meter x equal to. So click here, execute. So it is done also 16, 17. So we got all the nodes. Now we have to put here pin. So how to get those pins? Geometry, releases. So pinned. That means both end pins. So here this one will be both end pin. Both end pin. Here also both end pin. Here also both end pin. Now pinned one end. Here it will be pinned at one end. How to get pinned at one end? If I click here, I did like that. So you have to get like this. So pinned, again pinned here, pinned here, pinned here, already pinned are done. Here I have to provide pinned here also, here also pinned, here also pinned, here also pinned. So I am done. So if you look at very closely, you see here already I made the pin here, here. So pin is done. So there will be inflection point, moment will be 0 here. So I am closing this. So I am doing analysis again. Close. So we are done. If I go here, say results, diagram, moment, apply. Look at, now results are changed, especially this one. We have to check this one because they did this one only. So what it says, minus 99, 176, minus 99. Look at here. Still it is some difference, but very, very close. Look at here. Minus 99.86. Here it is 177.53. Here also minus 99.86. It is not exact because here 176, here 177. Here minus 99, here minus 99. So it is very close, but it is not exact. But I can make it exact value. How it is? I can make it exact value. How? Let's go to loads. Load table. Click on dead load for self weight. Remove this. Okay, now do analysis again. So it is done. Wow, you can see the value exact. Minus 99, 176, minus 99. Look at here, minus 99, 176, minus 99. Exact value. Now we can check the shear diagram. How it is? Remove this, put this FZ force and tick. Apply. Close it. You can see here 88, 110, because here also 110, so surely this is also 110, 88. Here it is showing 88, 110. Look at their diagram. 88, 110. 88, 110. So we got the exact value for the both cases. And be sure with this one, this type of structure, actually we do this procedure to make the indeterminate structure to determinant structures. That's what we have done here to get the approximate analysis. So our moment and shear diagram, we call it as, here it says, approximate shear and bending moment diagrams. So I think that's all for this structure. So we are done.